In this video, we're going to talk about Riemann sums. Riemann's sum. This is a key part in learning the basics of an equation because Riemann, he broke down a curve and he wants to calculate the area underneath the curve. What he did was he created rectangles. Without diving too much into the actual math behind it, let me just quickly illustrate how he found out the exact area underneath the graph. What he does is he created rectangles of equal breadths and of different heights. You notice that if I were to create 1, 2, 3, 4, 5, 6, 7, exactly 7 rectangles, the actual area underneath the curve is slightly more because I fail to so I'm calculating this. I fail to calculate the red color bits. So this creates an underestimation of the actual area underneath the curve, the sum of the rectangles. So sum of rectangles actually slightly less than the actual area. What happens when I do the same thing and within the same boundaries from A to B, I create more rectangles? This time around, I create 10 rectangles. Now, when I create 10 rectangles this time, my rectangles are actually skinnier. They are actually thinner. The underestimation actually shrunk down by a bit. And if we were to continue doing this, instead of using 10 rectangles, we use 100 rectangles, 500, 500,000 rectangles. When the number of rectangles increase to infinity, total area of rectangles tend towards the actual area under curve. This is the gist of Riemann sum. So of course now we have to tackle questions with actual math, not just this idea. Idea is very easy to understand. Just an extra point, we can also have rectangles that protrude out. So here, remember just now, our top left of the rectangle is touching and therefore is creating an underestimation. Now we can also make the rectangles touch from the right hand side, meaning like that. So these are known as right bound rectangles. The top right is touching the curve instead of the left. So let me just draw them side by side for a better comparison. So you have this left bound. However, the idea is still the same. When you have more and more rectangles, the overestimation will decrease to 0 and the total area of the blue color rectangles will be the actual area underneath the curve. So we are done with the first part. We have talked enough. Let's actually do a question. So many students actually find this chapter rather difficult because you have to be really secure with your summation. You have to be really secure with generating ideas and coming up with your own formulas. So let's take a look at this. This curve is actually x cubed plus 2, a very simple looking curve. Rectangles of width 1 over n. Now why 1 over n is because we are going from 0 all the way to 1 and there are n rectangles. So of course the width, if let's say I split into 5 rectangles from 0 to 1, of course the length of each one is 1 over 5, right? So now this time round, we don't know that it's 5, we only know that it's n. There are n rectangles. It's a general formula, that's why we have to use n. The width is 1 over n this time. We don't know how many rectangles are there. Given that this, show that the total area of n rectangles is this funny looking expression here. Don't think too much, just ask yourself, what is the area of one rectangle? Let's start off with the first one. What is the area of this red color one? The first rectangle would be just breadth times height. What is the height? The height is just simply 2. How do we get 2? Because the top left is actually touching the curve and it cuts at 2. Next rectangle. The next one here. How big is this one? To find out the height of this, all we need to know is when does it touch? It touches when x is 1 over n, right? So I'm going to zoom in here. You realize that this is 0 on the x-axis. This is now 1 over n on the x-axis. What is this point here? Just now, we sub in 0 into the curve, right? X cubed plus 2. So 0 cubed plus 2 gives you 2. What about this? To find this, all we need to do is sub in 1 over n, and we'll find the y coordinates, which turns out to be the height of the second rectangle. It would be 1 over n cubed plus 2 times the breadth, which is 1 over n. Actually, let me just turn this 2 around so that it's more consistent. So height times breadth, height times breadth. Next one, third rectangle. What would it be? What is this point here now? The third rectangle. To find the height, all we need to do is sub in 2 over n. Multiply by the breadth, which is still 1 over n. Of course, we can stop doing. Once you reach a certain point, you're comfortable with coming up with the general formula, stop doing and find out what is the last rectangle that you have to find. The nth rectangle, which is the last one, the area would be the breadth multiplied by the height. The height this time round, we'll be subbing in n minus 1 over n into the equation. So that would give us n minus 1 over n cubed plus 2. Your job now is to create a summation, because now we're supposed to sum up first rectangle with second rectangle with third rectangle, fourth rectangle, all the way until the nth rectangle, right? So instead of writing this plus this plus this plus this, are we able to generate a summation here, all rectangles? You have to notice some kind of number pattern. This number 2 here is the issue, because this is just 1 over n cubed, 2 over n cubed. The next one will be 3 over n cubed, so on until the nth, which is n minus 1 over n cubed, right? So I have to rewrite this as this for a more consistent formula later. So now once you have written the 2 as 0 over n cubed plus 2, then it becomes very easy, because what is the moving part here? The moving part here is this item. Everything else remains exactly the same. The moving part will be known as your r. Everything else is fixed. And now r starts from what? R starts from 0 to n minus 1. It starts off from 0 all the way to n minus 1. Once we are done with this, we will be doing some manipulation to actually help us solve this question. Here you get r equals 0 to n minus 1. Here you will take out the 1 over n because it's just a number. And you're left with r cubed over n cubed. In fact, you can also take out this n cubed and put it outside to give us 1 over n to the power of 4 plus summation of 2 over n, which is this times this. I'm going to split it into 2 summation. Next, let's take a look at this, the second one, the easier one. What is summation of 0 to n minus 1 when there are no r's inside? Every single term is just 2 over n. So the correct answer is 2 over n multiplied by, how many terms are there from 0 to n minus 1? There are n terms. This part is done. We're not touching it ever again. Now, this one, slightly more interesting. You have to make use of the formula that they gave you. Summation of r cubed from 1 to n is this. What if I want to go from 0 to n minus 1? Summing from 0 to n minus 1 is exactly the same as, so we start off with 0 cubed plus 1 cubed. Now 0 cubed is actually 0, so it's as good as summing from 1 to n minus 1 of r cubed. That means that instead of going up to n, I'm going to go to n minus 1. The formula, let me just copy it down. Summation of r cubed would be n squared over 4 n plus 1 squared, right? I'm going to only go until n minus 1. This would give us n minus 1 squared over 4 n minus 1 plus 1, which gives us n squared. Here I will get 2. Simplifying this would give us 1 over n to the power 4 n squared n minus 1 squared over 4 plus 2. Okay, let me just expand this mess right here. This is 4n power 4. Above I'll get n squared n minus 1 whole thing square, which just be n squared minus 2n plus 1, and then we add a 2 behind. Simplifying this further would give us n to the power 4 minus 2n cubed plus n squared over 4n power 4 plus 2. Split this into 3 fractions, I will get 1 over 4 minus, this cancels to give us 1 over 2n. Here, cancel to give you 1 over 4n squared plus 2. Gather the numbers up, I'll get 9 over 4 minus 1 over 2n plus 1 over 4n squared, which is what the question asked you to show in the first place. Now, last two parts, we will have to make use of the concept from the very beginning that to estimate the actual area underneath the curve, we will need the number of rectangles to go to infinity. I want as many rectangles as I can. Right now, we have n rectangles. Is n rectangles enough? Not enough. We actually need for n to go to infinity in order for us to find the exact area underneath the curve. So we already have area of rectangles equals to 9 over 4 minus 1 over 2n plus 1 over 4n squared. If there are 3 rectangles, we will sum in n equals to 3. If I have 20 rectangles, I'll sum in n equals to 20 to find the area. But 20 rectangles is still an underestimation. How many rectangles do we want? We want infinitely many. So as n goes to infinity, area would be 9 over 4 minus 1 over infinity give us 0. 1 over 4 infinity square will also give us 0. So the answer is simply just 9 over 4. 1 mark. Very easy. Find the least value of n such that area is no less than 99% of the exact area. This one is slightly more interesting. I want the actual area of rectangles to be no less, meaning more, than 99% of the exact area. So this will be 0.99 of the exact area. What is the least value of n? So this simplifies to just a simple inequalities question. 9 over 4 minus 1 over 2n plus 1 over 4n squared greater than 0.99, 9 over 4. Go to your GC, plot in this graph, plot in this. So once you have put both of these graphs onto the GC, then you will get something like this. Go to graph, get this funny looking graph. Now remember, we are looking for an n value such that the blue graph, which is the one on the left, when the blue graph first exceeds the red color horizontal line. So we expect this n values to be positive because n represents the number of rectangles. So we have to adjust our window a bit. For minimum value, for x, I'm not interested in negative values. So let me just start off with 1. X max would be, let's say, 35. And for minimum y value, we are actually only interested in this value, right? Which is where you can see the horizontal red line. So I'll just put between 1 to 3 because this is 2 point something. Let me hit the graph again. Let's see what happens. So you see there has to be an intersection. So let's go ahead and find that. Calculate the intersection. Turns out the intersection is 21.7. Go to your table. That means the answer is either 21 or 22. Going to your table, go to x equals to 21 and check whether this fraction it's actually greater than the red one, or is it 22 where this fraction it exceeds the red color value? Turns out the answer is this: 4313 over 1936 is the first time the blue color value exceeds the red color value. So your answer would be n equals to 22. When there are 22 rectangles, the estimation of the exact area underneath the curve is already 99% accurate. Okay, that's it for this video.